In this video, let's look at systematic decomposition. This is a method of programming. Basically, we got this little guy over here. He pops up with a beautiful idea, which then he turns into a step-by-step procedure. The procedure must be finite. In other words, it must terminate. It must be definite. In other words, each step is precisely stated. And it must be effectively computable. In other words, each step can be carried out. Stepwise refinement. This is also known as systematic decomposition. We start with a problem statement. For example, write an assembler program to play the game of Simon using the LEDs and push-button switches. We decompose the task into a few simpler subtasks. We decompose each subtask into smaller subtasks, and these into even smaller subtasks, etc., until you get the machine down to the assembly language or machine level. And we incrementally develop the program, and we test, and we test, and we test. And it's somewhat iterative. So how do we make a good problem statement? Because problem statements are written in English, they're sometimes ambiguous and or incomplete. For example, how is the game played? How many LEDs start the game? When switches, which switches and which LEDs? How long is an LED on or off? What happens when an error is made? What happens when a sequence is successfully reproduced? How is a new sequence started? So how do you resolve issues like this? Well, there's several ways. You could ask the person who wants the problem solved, or you can make an executive decision and document it. So let's look at a Simon example. Well, the problem statement says, play the game of Simon using LEDs and push-button switches. I'm going to use systematic decomposition. So here's an algorithm. We're going to initialize the Simon board, set up a new game, input random sequence of tones and LEDs, or output a random sequence of tones and LEDs, reset the sequence, get and compare the player's response, and then we'll output the results and restart with a new game, a new sequence. So here's some pseudocode, kind of in C, kind of with labels there put in. So this whole thing is in a big while loop, so we got that on the outside. Then we've got the set up the new game thing, basically, which figures sets up how many tries you have, and it says you start out successful, and it saves a random seed that you're going to need to use to output the random sequence of tones. And then we're looking at while we're successful. So we store the random seed, we increment the tries, and we go into a little for loop. For I is less than the number of tries. So you get the random thing, do the LED tones. And then we do the player, and so we start again on the same thing. And we go through a little for loop down there, getting the switches. And we do the tones. And if the switches are right, then we say okay, but if not, we say that success is false. So after we're done with that little part, we go down to do the results, and we if we have success, we output success, otherwise raspberry. So how do we change this pseudocode into something more like assembly code? So we do incremental development. So here we go. We're going to use a lot of subroutines. We'll fill in those subroutines as we get to them. So we call the subroutine init the board, and then we got this new game, and we call the new game and save the random seed and so on. Look at all those, basically just like what we were doing before. We can convert that pseudocode into assembly, and we go through all the things, and we just keep cranking. And that's basically, kind of an example of how you program an assembler.